In this video, I thought I would talk about some of the homework problems that we get in these PhD level topics courses in mathematics. So just as a reminder, I'm taking a course in convex geometry this semester, as well as a course in Fourier analysis. I had signed up, I'm also taking a measure theory seminar, but it's not so much a class as it is a seminar. You go and you listen to people talk about their research. But I was signed up for a graduate level statistics course, and unfortunately I dropped it. I think that it would be beneficial to give myself more time to read books that are within my field of study, because statistics is an applied math course and I'm in pure math. I didn't need to take the class, but I took it because I thought it would be beneficial to me in the long run. But for various reasons, I decided to drop it and focused more on research and meeting with my potential advisor. I say potential because it's basically, we're pretty much going to work together. It's just, we need to sit down and basically sign the paperwork. That's why I say potential. Anyway, so I'm going to show you my homework from Fourier analysis, because we get homework problems regularly in the course. A lot of these topic classes, they don't really, they're kind of informal. They go in, they talk about the stuff that they're interested in, and then if they want to give you like a test or whatever, it's usually like one problem over some famous result from the course. It's pretty chillax, which I appreciate. Okay, so this is the Fourier analysis course. If you want the reading list that he has here, these are the authors and the textbooks that he recommended. I mentioned the Katz-Nelson book a lot because it is the book that I had prior to the class, and I've read through it a little bit, so I'm partial to it. But these are the other ones. I don't think I'll read them. Maybe in the, years down the road, I'll pick them up. But the Katz-Nelson book is the one I'm trying to get through. And so remember, the way that this guy grades is that he gives us points for doing homework problems. And if we solve 4, we get an A in the course. So far I've basically solved 2. I say basically because well, I'll explain later. But I've done 2. I've done 2 problems so far. And 4 problems sounds kind of like a student's dream, right? They solve 4 problems, they get an A for the course. But the problems are very difficult. So that's the catch. And then some of them are easy, in which case those guys go by fast. Everyone wants to do the easy problems. So here are the homework problems, in case you're interested in solving some of these yourself. So problem number 5, I'm going to skip the first 4 because these were the batch. These came in as a batch of problems. He gave us all of these at once. So problem number 5 says, show that there exists a sequence of complex numbers that tend to 0 as modulus n tends toward infinity. So again, n can be a negative number. Think of it's an integer. N is an integer here. So when n gets large, the sequence decays. So show that there exists a sequence such that there does not exist an L1 function with Fourier coefficients at ak. I don't know why I switched from k to n, but apparently I did. So I believe this problem is solved in Katz-Nelson's book. He gives an example, and I think the example is an is equal to 1 divided by log n, but I have to check to make sure that's correct or not. I'm not entirely sure. I think that works, but I did not do this problem at the board. Someone else did. Homework 6. Show that there exists an L1 function such that the sum of Fourier coefficients tends to f0, but f fails the Dini criterion at 0. So the Dini criterion says that this expression is not, well, okay, I guess if it satisfied Dini's criterion, then it would be an L1 function, but this means fails. So this is not an L1 function. I have not done this problem. Homework 7. I think he said that homework 7 was one of the more challenging problems, or at least at the moment, because I think it uses some machinery that we haven't talked about in class, because these homework problems are intended to last, several weeks into the semester. We're not supposed to be able to do all of these all at once. So it says that suppose f is a Holder alpha function with alpha positive. Show that there exists an m such that if you convolve f m times, then it is a C3 function, meaning that it has a continuous derivative, or continuous third derivative, or 3 times differentiable. I don't know which one I'm trying to say. 3 times differentiable function. And then homework 8 is an extension of 7. Construct a function f that is continuous, such that for every m, if you convolve f m times, it is not a C1 function. So I definitely have not done 7 and 8. I wish someone would. I'm kind of interested in seeing how to do it. But I think it's outside of my capability right now. Homework number 9, let f and g be L1 periodic functions. So just for clarity, the period that we use in class is the interval from -1/2 to 1/2. You don't have to use that period, but that's the one that he likes. And after being in his class and reading through some books, it's the interval that I like too. I think it's whatever. It's just what you're used to. Assume that the support of f is contained in this interval and the support of g is contained in that interval. So if you're not familiar with support, it's just wherever the function is not equal to 0, which means that outside of this interval, f is identically equal to 0, and same story with g. Show that the sum of the product of Fourier coefficients, where this represents the conjugation of g hat, that this product, when you sum it, gives you 0. So I attempted number 9, and I think I got really close to the answer. I did not present it at the board because I think there's a mistake in it, and I'm trying to fix the mistake. I have not looked at this problem since I worked on it, which was like 4 days ago, but I might try and work on it more this week. Problem 10. Is it enough in homework number 9 to assume merely that the intersection of supports is the empty set, meaning that they have disjoint supports? So it's the same as homework 9, except now instead of assuming this, you're just saying, okay, these two supports don't touch one another. I believe the answer is no. It is not enough to assume. And my gut reaction is always to go to like rationals and irrationals. Like suppose that this is the set of rationals between -1/2 and 1/2, and these are the irrationals between those two numbers. I have not played with it, but my gut feeling tells me that that's probably what they're looking for, but I really don't know. I have to go through it again. Homework number 11. Suppose f is an L1 function, g is continuous. Does it follow that the sum of f hat times g hat bar over integers k is equal to the integral of f times g bar? So this looks a lot like, I believe, Fayer's theorem from Katz-Nelson's book, or any Fourier analysis book. It's a famous theorem. It looks like it, but it's not it, because they assume that g is also L1, and here we only assume that g is continuous. I have not played with this homework problem, but that's what it reminded me of. I think it's Fayer's theorem. You have to correct me on it, but I remember reading the theorem in the book where this is mentioned. Okay. So homework 12. Homework 12 was the one I attempted at the board on Thursday. Well, you are given a sequence of positive or non-negative real numbers. They decrease to 0 as n tends toward infinity, and you assume that the sequence is convex. So mathematically, this is what convex means, but in the context of geometry, it starts here and it bends downward like this. It tapers off. So it's not like a straight line. It bends downward like that. Show that the sum of these guys times that represents a non-negative L1 function. So essentially, there's an L1 function such that this is the Fourier series of that function. Okay, so when he wrote this at the board, I immediately wrote Katz-Nelson next to it because I've been reading through the book, and when he wrote this, I was like, this sounds like a lot like a theorem that Katz-Nelson talked about in the book. So like that night, I got out that book and flipped through it, and I did find the theorem where this was mentioned. It was pretty much identical to this statement, but it was worded slightly different, but it was the same problem. It was the exact same problem. So I wrote down the proof from Katz-Nelson. It was pretty short, but he left a lot of details untalked about, or not talked about, which kind of scares me because you don't really want to go up to the board and not know what you're talking about. So I opened up the Graphicos book, the big red one. It's like 900 pages. Flipped through it, and I found the same problem in there proved, and he goes into a lot more detail. So I tried following Katznelson because I just like the book better, and supplementing it with the stuff from the Graphicos book. And when I presented this problem at the board, it took me like maybe 20 to 30 minutes, I think, to get through it. And there was one step at the very end that was true, so I believe I got credit for it, but then someone asked me to elaborate on it a little bit more, and I struggled to elaborate on it. It was, because sometimes when you're at the board, you just can't think straight, and I know in the Graphicos book, he doesn't elaborate anymore because it's kind of, I don't know why he doesn't. You choose which details to put in and which ones to leave out. But I believe that what I had written was sufficient enough for credit, so that's why I put the tally mark there. But I think in a future lecture, when we go up to the board, I'll probably have to comment on it a little bit more just to make sure that all ends are tied. It's kind of a strange way, I admit, to grade students, but it is the way that the class is run. Okay, so if you're interested in attempting those problems, go right ahead. They are difficult. Some of them are easy. But I thought I would show you some of the stuff that I've been working on for the homework. Okay, so this was all stuff that I thought I might need for, wait a minute, that is a Fayer's theorem. Okay, I guess it wasn't Fayer's theorem, was it? Was it? Oh, who cares? I don't know. It's just, you don't really want to go up to the board with details lacking, because then you'll just die a horrible death up there. And, you know, that proof requires Fayer's kernel. We hadn't talked about Fayer's kernel in the class, so I was afraid that I would have to derive all that stuff. But he told me that he was going to talk about it that day, so I didn't have to do it. So I'm not entirely sure sometimes of what I'm supposed to justify and what I'm allowed to use as a free lunch. Okay, so question number 9. This is what I had written. I believe there's a mistake in it. I have not looked at this problem in 4 days, so I may work on it this week and try and present it on Thursday. So you can read the statement up there, and I'll just go through what I've written for the proof. So I've written down the definitions of f hat and g hat, the Fourier coefficients of those guys. I think I probably played a little bit too fast and loose with the positives and negatives in here. So I probably switched a sign that really doesn't need to be switched. There probably should be a G bar on G. I don't know. I have to go through this again. I'm a little bit scatterbrained when it comes to this stuff. So really, I just wanted to write down the definition, and I wrote down the definition of convolution, and that by definition, the Fourier coefficient of the convolution is this guy. That's just definition. And this was a result from class. So we have that. And my goal was to show that if this is somehow 0, then the sum of those guys is also 0. And so I used this claim that the support of the convolution is contained in the sum of supports. This is the Minkowski sum, by the way. And this is a proof that was on the internet, and I just copied it down. And then if you actually do the sum of supports, then I believe the support of the convolution is this interval. I have to check this, but I think it's correct. And then from this, you can change your limits of integration. And then move, I didn't like this, so I moved down here. And I believe I just applied this result down here, and then through algebra I showed that this was equal to 0 times 0. I'm a little bit scared of this because f has support only at -1/6 and g has support at +1/6, and since it's the Lebesgue integral with respect to the Lebesgue measure, you integrate over a single point, you're going to get 0. So I think this might be equal to 0, in which case you're summing up countably many zeros. So everything should be kosher. But I don't really know, because when I was done writing this up, I recognized that I had dropped the conjugation bar here. I was like, oh, crap. I probably screwed up all this then because I forgot about the conjugation. And then I just went in and haphazardly threw in a bunch of positives and negatives. That's my biggest problem, I think, as a math student. And then I just kind of was like, well, I'm not going to present this on Thursday. I'll deal with it later. So then I put it aside. Anyway, so I'll work on this some more later. I think this problem is definitely within my wheelhouse. I just have to go through it slower and not make a bunch of silly mistakes. Anyway, so that's what homework is like.